We will start from classical mechanics and show that there is no such thing as quantum tunneling, of course, in classical mechanics, because we have to consider a potential energy in particular. And I will consider a rectangular barrier, a rectangular potential if you want. What is a barrier? Now let me explain it. We have something like this. So here we have a potential which is constant in the interval 0, L. This is the x axis, and this is the function v of x, which is equal to v0, let's say, if x belongs to the interval 0, L, and it is equal to 0 otherwise. Now, if the potential is positive, it means that it is repelling a particle coming from the left, for example. So let's assume that the particle is coming from the left, and when it encounters this barrier, it will be repelled if the particle does not have a sufficient amount of energy. In particular, the energy of the particle is equal to 1/2 the mass of the particle times x dot squared, which is the velocity squared, and this is of course the kinetic energy, plus the potential energy here, v of x. And in particular, if we consider the interval 0, L, of course this will be equal to v0. And therefore we have E minus v0 times 2 divided by m. This is equal to x dot squared. And you can see that this quantity here should be always greater than or equal to 0, because of course the velocity squared is greater than or equal to 0. But this means that, for example, if we have that the total energy of the system less than or equal to v0, this means that the particle cannot penetrate the barrier. Now let me explain it a little better. For example, let's assume that the particle is starting here, somewhere here, with some kinetic energy, and the kinetic energy of the particle there is just 1/2 m x dot squared at the initial time. It is some initial kinetic energy if you want, so x dot 0 squared, and this is equal to the energy, but the energy is a constant, right? So this energy will be preserved because we are considering just a very simple system. There is no dissipation of energy, okay? So the energy will remain constant, and if this energy is less than v0, it means that the particle doesn't have enough energy to penetrate the barrier. Now, if you want to understand the situation in terms of forces, we know that the force, which depends in general on the position, will be equal to minus the derivative of the potential energy with respect to x. And now if you draw the forces on the system there, we have something like this. So when we take the derivative of a constant, we will get 0, but we have to be careful when we take the derivative at x equal to 0 and at x equal to L, because there, when we take a derivative there, we have a discontinuity, okay? So we will get some infinity here, and in particular we will get minus v0 times the Dirac delta of x, because when we consider the derivative at x equal to 0, we have a step. When we consider the derivative of a step, there we will get a Dirac delta, and with a minus sign because of this here. Also, we will have a positive Dirac delta here equal to v0 times delta of x. When we have a negative force here, it means that the force is pushing the particle to the left of the x-axis, in the negative direction of the x-axis. Whereas when it is positive, it will push the particle to the right. Okay, so it means that when the particle is approaching the barrier, it will feel a force here that's going to thwart the motion of the particle to the right. So it will oppose that motion, and it will repel the particle if the energy of the particle is not sufficient enough. What we want to do is we would like to see if this occurs in quantum physics as well. And we will see that this does not happen. So there is a probability that even if the particle does not have enough energy on paper, it is still possible for the particle to penetrate the barrier. There is a non-zero probability, and we will see that this probability will depend, of course, on v0, but also on the width of the barrier, which is equal to L. Okay, so this is very important. We will calculate this probability. And of course, in quantum physics, we don't have the same equations. We will have to use the Schrödinger equation instead of F equals ma in classical physics, right? This F equals ma can be written as F equal to m times the derivative of the velocity, which is x dot over dt. And if you multiply this by dx, so we have f dx equal to m dx dot times dx, and we also have to divide by dt. So I can divide dx by dt, right? And this is equal to x dot here. Now if I consider the definition of the potential, right? So I defined the potential energy like this, right? So we know that dV, the differential of the potential, is equal to minus the force times dx. So here we have minus dV, and from here you get that minus dV equal to, we can rewrite the right hand side as the differential of m times x dot squared over 2, which is the kinetic energy. And from here we can see that we get the differential of mx dot squared over 2 plus v is equal to 0, which means that this quantity here should be equal to a constant, and we know that the constant is just the energy E. Okay, so from the law F equals ma for just one particle, we can see that the equation of the energy can be derived. Okay, so we have implicitly used the equation F equals ma, but the analog of F equals ma in quantum mechanics is the Schrödinger equation. Okay, so we have to use the Schrödinger equation to solve the problem. Okay, and we will do that in steps. It will not be complicated, but we have to be more patient in that case because it will take more time. And finally, we will have to calculate the probability.